disorder. So anytime the ball rolls back and forth, it's doing some work, and then if we don't supply more energy after a few minutes, they will stop. So it depends on how big the ramp is or how the pendulum is. So in other words, if you have like a pendulum that's focused pendulum, which was 67 meters, it will last almost a day. But the little ones, after a few minutes, go out or they stop because they use their potential energy to kinetic and back and forth, and in between always there is a work, and that's why the entropy increases and the ball stops. As I mentioned a few minutes ago, I had to bring very important factor in Galileo's formula, and that was kinetic energy. But unfortunately, kinetic energy, when Galileo did this, had not even been discovered. It would take another 200 years, and then her name was Amélie du Châtelet in France. She was self-educated, one of the greatest scientists at the time. She discovered that, and the reason why she discovered that, because her husband, Voltaire, was one of the greatest scientists at the time. Then he was in Holland and then discovered one scientist, his name was William Gravesande, and then despite the public perception, people would think that, if you drop the ball, your velocity is doubled, your ball will travel 2 times more, and then Gravesande, the Dutch physicist, proved the otherwise. He said, if the ball has twice the speed or velocity, will propel 4 times more. And that was a great idea. So Voltaire called the wife and told her that this is the idea, and she was so smart, she took advantage of this. Then she came up with the formula, kinetic energy, half of the mass times velocity squared. But I had to bring this in a Galileo's equation. So what I did, I calculated for Moon, Mars, Earth, and Jupiter. Well, of course, the way I calculated, I could not use ramp. But what I did, I got their acceleration, and then I calculated, and then I saw very important pattern. The pattern was exactly like the ramp. The way, this is called position. See? The first second on Moon, the position is exactly 80 centimeters. The reason why, the Moon has acceleration due to gravity 1.6 meters. So in other words, it's like 1/6 of Earth. On Mars, it's almost 1/3 of Earth. On Mars, the acceleration due to gravity is 3.7 meters per second. So you can see the first second is 1.8 meters. And then on Earth is exactly 9.8, and half of the 9.8, according to Galileo's, is 4.9. And on Jupiter is exactly 24.8 meters per second squared, and the half of it is exactly 12.4 meters second. And then I did it all the way till 8 or 10 seconds. I realized they match perfectly with Galileo's ramp, and it doesn't make any difference. It doesn't matter how the gravity is, like Moon is 1.6, or Mars is 3.7, or Earth is 9.8, or Jupiter is 24.8. You can see the pattern is exactly the same. I give you one example. Like on Moon, 3 seconds is 7.2 meters. The reason why is 3 times 3 is 9, and 9 times half of the acceleration is exactly 7.2. See? On Mars is the same way. 3 times 3 is 9, and 9 times 1.8 is exactly 16.65. On Earth is the same way. 3 times 3 is exactly 9, and 9 times 4.9 is exactly 44.1. So is on Jupiter. And then I saw that same pattern, and then I realized it doesn't make any difference. That's what Galileo did. So he had to use his incline or his ramp. So he had it with more angle, less angle. Then he realized nothing is changing. Everything is proportional. So this is what happened. I also had to use elastic collisions. The reason why I did this, because my ramps were so slow, so I could monitor exactly what happened if I have elastic collision. Why did I do this? Because I had same masses, like 16 grams here, 16 grams here, and then when I rolled them down after the collision, so you can see that 16 grams propelled itself 30 centimeters upward to the opposite direction. And then when I increased the mass or doubled the mass, I had 32 grams, so I rolled them down, so just after the collision, it propelled it exactly 45 centimeters. So of course I have to explain, when the mass is increased, kinetic energy, according to the formula, is exactly 4 times. But unfortunately, it's not like this. It's 1.5 times. As you can see, the reason why is doing some work. And besides, all these experiments have to be done in vacuum, which is so expensive. I can't do that. Always we have air here, we have air track, so we couldn't do it. So this one, as you can see, after the collision is going to be more because the acceleration due to gravity is double on this one. So it's 1 meter per second. So when 16 grams is colliding with 16 grams, it propels exactly 40 centimeters. But see, when 32 collides with 16 grams, see, it propels itself 60. So instead of 80, it propels 60. But I have to explain something else. When we have a collision like this, they call it elastic collision. Why did I choose the steel balls? Because they are amazing. They are so precise. They're factory made, and then their velocities are good, and then their elastic collisions are good. The deformation is extremely small. So what happened after the collision? The momentum and also the kinetic energy is exactly like the pool ball. When I have the cue ball and then hitting the other balls and the other balls, and then cue ball stops, but the other balls propels according to the force exerted. I also made 3 pendulums. I will explain in a minute. So one of them, the length was 25 centimeter, and the other one 50 centimeter, and one was exactly 100 centimeters or 1 meter. So what did I want to do here? What I wanted to do here, compare this with the ramp to see if I have like 36 grams swinging back and forth here on 25 centimeter, and then I compared 36 grams swinging back and forth on 50 centimeter compared to 100 centimeter. So what I did, you can see these shaded areas. So each one, see, is 30 degrees, 45 degrees, 60 degrees, and 90 degrees. So you can see I had a stopwatch. So what I did, I released the ball or the bob from here back and forth, and then I started my stopwatch. By the time this gets to this here, then aligned with the, because I released the ball from the top here. By the time that 36 ball aligns with the 60 degrees, so I stopped the watch, and then I realized in 25 centimeters, it makes exactly 102 periods. And 72 grams makes exactly 152 periods. So I repeated the experiment with 50 centimeters, and when I realized that 50 centimeters, 36 grams made 88 periods, but with 72 grams made 132. But this is the important part. When I divided the 154 periods to 102 on 25, I realized instead of 2, it's exactly 1.5. So according to the kinetic energy, this was supposed to be twice as much, but it's exactly 1.5. So this corresponds exactly the way I did it on ramps. So according to kinetic energy, KE is equal to half of the mass times velocity squared. When we increase the mass double, and the kinetic energy is not double. I also theorized Galileo's formula, which was uniformly accelerated motion, which says distance is equal to half of acceleration times time squared, is in some respects exactly like translational kinetic energy, which is half of the mass velocity squared. But I had to do some experiment in order to prove this, and the reason why I did this, just wanted to demonstrate that mass can become acceleration and acceleration can become mass. So what I found out finally was half of the acceleration is exactly half of the mass. So as you can see, this is ramp A and this is ramp B, and my ramp A, as I explained before, is 50 centimeter per square. 50 centimeter second square. But that one is 1 meter square, 1 meter per second square. So as you can see, the ball takes exactly 2 seconds to get to the finish line or the center, and 2 seconds back, because the acceleration is so slow on this one. This is almost 1/20th of the Earth. But that one is 1/10 of the Earth, so the ball takes exactly 1 second to the center and 1 second right there. As you can see, I rolled down 56 grams to collide with 28, which is the half of it, and then it propels the other side is exactly 45 centimeters. So here what I did, I increased or I doubled the acceleration, but I reduced the mass, or in other words, I did it 28. So what I did here, 28 collided with 28 grams, it just propels exactly 45 centimeters. So you can see here, I reduced the acceleration to half, but I increased the mass double, but here I reduced the mass, but I increased the acceleration. As you can see, they all matches perfectly. Like 112 grams colliding with 28 grams, you see 56 grams colliding with 63 grams. This is another experiment I will demonstrate in a minute. So I made this exactly the way it is. So it's a hammer. As you can see, the hammer is exactly 500 grams. And then there are 3 nails. They're all almost half. So they're not completely in. But as you can see, when the hammer slow down, when I put the hammer on top of this nail, it's not going to do anything because it's only 500 grams. But as I release the hammer from here, which is 90 degrees, and the velocity, or it takes exactly half a second, that drove the nail exactly 1.5 centimeter. So you can see I can repeat the same thing by lowering 10 kilogram mass slowly. It will exactly push this exactly 1.5 centimeter. But if I have 20 kilograms, I can slowly put it on this, then it will drive the nail all the way down. So you can see here something important. Mass can become acceleration, and acceleration can become mass. So here, if I put that 500 grams on top of this nail, it's not going to do anything. But the same mass, 500, when it accelerates, can do the work of almost 10 kilograms. So this is the way that works. But of course, I will demonstrate in a minute. second square, and that one is 1 meter per second square. Now what I did here, see, you can see those two lines. Each one has 5 centimeters toward the center, so is that one. So I have to use my stopwatch, so I just use this 72 grams, and then I roll it back and forth and back and forth. By the time they align to here, so in other words, they used all the kinetic potential energies. So when I recorded my time, it was matching perfectly with the half of, so you can see 72 grams here, 36 grams here. They match perfectly. I have to explain this more, and as I said, this is the interchangeability of mass and acceleration. So in other words, acceleration can become mass, and mass can become acceleration. So as you can see, 72 grams took exactly 202 seconds on this ramp, and then 36 grams took exactly 202 seconds on this fast ramp. So was 40 grams and so was 20 grams. But unfortunately, my experiment might take like 3-4 hours. I have to demonstrate some of them because we are not going to wait 20 minutes for each experiment. And as you can see, the determining factor here is kinetic energy, because the acceleration due to gravity, see, on this one is half, on that one is more. And even though acceleration due to gravity on Earth is 9.8, but my ramp has amazing advantage. I can manipulate the acceleration due to gravity. So I can do like I'm on Mars, I'm on Moon, or I'm on Jupiter. I can increase and decrease the acceleration. Why did I do this? I just wanted to prove that always mass can become acceleration and the acceleration can become mass. As I said or theorized, the most important thing for rolling balls on a ramp or pendulum or falling objects is the mass in motion and kinetic energy. As you can see, this is translational kinetic energy, which is half of the mass times velocity squared. If we increase the mass by 2, the kinetic energy is going to be 2, and as I did with my experiment, it's not going to be exactly 2 due to the second laws of thermodynamics, which is disorder. So always we get 1.5 instead of 2. But this is important. If we increase the velocity in kinetic energy, and then the kinetic energy is 4 times. See, if we increase that by 4 times, the kinetic energy is 16 times. And I discovered something extremely important. I realized this kinetic energy fits perfectly with ramp, with pendulum, and falling object. And then I realized it doesn't matter how much our acceleration is, or how fast or how slow, kinetic energy works perfectly. So in other words, each second we have like a position of ball in first second, second second, third second, and fourth second. It matches perfectly with the kinetic energy. This is another experiment, as I said before. I made 3 pendulums, one 25 centimeter length, one 50 centimeter, and the other one is 4 meters or 400 centimeters. See, as you can see, the way I said, kinetic energy is half mass times velocity squared. If we increase the mass by 2, the kinetic energy is times 2, but if we increase the velocity by 2, the kinetic energy is 4 because this is squared. So as you can see here, on 25 centimeters, the pendulum moves back and forth or swings back and forth, and each, see, 90 degrees exactly 25, it's 1/4 of a second, see? And then back and forth, it exactly makes 1 second period. So in other words, it's 180 degrees, and 180 degrees or 2 pi makes it exactly 1 second. And on 1 meter is exactly 2 seconds, because 90 degrees takes half a second, another half a second, and then times 2 is exactly 2 seconds. And you can see the velocity on this one is 1.57 meter. Velocity on 1 meter is 3.14 meter per second. The velocity on this one, which is 4 meters, well, like I said, I have to mention this. I have to do this 4 meters in the big warehouse because my ceiling is maximum 3 meters high, so I couldn't do it. But I will explain what happened. So the velocity on 4 meters is exactly 6.28. So divided by this, divided by 6.28 meters. So I wanted to make sure that the kinetic energy works exactly the way it works on